Everything clear? Okay, very good. So last thing I did yesterday was basically arriving at the parton model, naive parton model expression of the structure function, where we concluded that in general, say a structure function f2 of x and q squared divided by x can be written as a convolution dy over y from x to 1 of a coefficient function c of x over y and q square and the PDF q of y, where this c x over y and q square was actually the structure function f2 divided by x computed for an incoming quark hitting the, so this guy here is nothing but this guy here with an incoming quark with momentum y times p, because x over y is like, sorry, this is x over y, of course, f2 q square to yp dot q and q square. Okay, so this was the kind of parton model conclusion that we reached yesterday. So what I'm going to do now is upgrade first to what is called the QCD improved parton model, and then go an extra step and actually show full-fledged QCD factorization. So in order to do this, we have to take a closer look at what happens when we try and compute. Yeah, everything is okay. Yeah. Take a closer look to what happens when we try and go beyond leading order. So remember the way we derived this expression. So in particular, the way we arrived at the conclusion that the coefficient function is just the structure function computed for a free quark, was noticing that if I compute my operator matrix elements in a free quark state, then the PDF becomes a delta function, right? And then I just got the identity, which is here, right? But how do I reach the conclusion? When I did it yesterday, I told you that the way to conclude that the PDF is a delta function, or if you wish that all the reduced operator matrix elements in a free quark state are equal to 1, was to use the Dirac equation, right? So I told you something like, well, if I take a free quark state with momentum p and I evaluate my leading twist operators, which you remember are something like psi bar, gamma mu 1, partial derivative d mu 2, d mu n q p, this is just some a n p 2p mu 1 2p mu n with all a n's equal to 1, and I told you you can show that this is the case using the Dirac equation. But you know, come to think about it, we are doing quantum field theory. We are not doing quantum mechanics. So the Dirac equation is like zeroth order quantum field theory. So what we should really do, if we want to calculate the operator matrix element in a free quark state, we are doing this in an interacting field theory anyway. So what we are supposed to do is calculate Feynman diagrams. So how do the Feynman diagrams look like? Well, you can think of this state here and this state here as being a creation operator acting on the right, and a creation operator acting on the left, which is an annihilation operator. And then you use Wick's theorem to calculate this matrix element. So basically what you're doing here is you have the incoming and outgoing states, and here in the middle you have the matrix element of the operator, and at leading order this is the only Feynman diagram that you have, which means you pick up a creation operator from this guy, an annihilation operator, I'm sorry, there was a field sign missing here, an annihilation operator from this guy, you contract them with the state here, and then you have a Dirac spinner, and then you use the Dirac equation, like I said yesterday. But this is just leading order. This is an interacting field theory. Here in between, you have the interaction, the full-fledged interaction. So at next leading order, you start having Feynman diagrams that look like this, of course. And then you have more. In fact, you have, so let me keep going with next leading order. You have a diagram like this, of course. And then, well, the same one with the loop on the outgoing line. And then look, I mean, here you have a partial derivative, which is actually covariant derivative. Remember, d mu is actual partial mu minus I e a mu, where a mu is a gauge field. So you even have diagrams that look like this, where by this I mean that the gauge field starts here and ends up on the covariant derivative inside the operator, right? So you have to sum all these diagrams, and they are all loop diagrams, and it's easy to see that they are all divergent diagrams. I don't have time to actually do the calculation. You can find it in Peskin's book, for example. It's, there's nothing mysterious in this calculation. You just put in the final rules, you just do it, and you discover that they diverge. So what do you do when you have divergent diagrams? You have to renormalize the operator matrix element. So take care. These are all different operators. So you actually have to renormalize each operator with its own renormalization constant, which you expect because these are composite operators. They have two fields, right? So the product of two fields in the same space-time point is a highly divergent thing. So you do expect these matrix elements to diverge. And then what you're really saying is that n, the reduced matrix element which you got here, is defined as renormalized, an renormalized, which is an bare, divided by an bare, evaluated at some scale mu square, which you can write as an bare times zn, where zn is nothing but 1 over an bare at mu square. And then what this means is that an renormalized at the scale mu square is equal to 1. Okay, so this is like what you do when you define, say, a renormalized charge. What is the renormalized charge? Well, the actual charge is not the parameter you write in the Lagrange. The actual charge is what you measure in experiments. So you define the renormalized charge as what you get when you compute the Feynman diagrams by setting that the value you have is what you would get at some particular reference scale. And this is just the same when you renormalize an operator. So at this point, of course, what happens is that we are guaranteed that these ANs are all equal to 1 because we divided out by their value, but of course they are all equal to 1 at one particular reference scale. They won't be equal to 1 at all possible scales. And this then means that the operators which appear up there, so remember the operator matrix elements are actually, so the ANs are the Mellin moments of the PDF, all right? So these guys now renormalized are the Mellin moments of a renormalized PDFs. They acquire scale dependence, which means that the PDF has acquired a scale dependence. So let's try and understand how this works, okay? So first observation, if I take a derivative of the renormalized an with respect to mu square, I get something which is actually proportional to an itself, and it has a coefficient of proportionality that can only depend on the coupling of the theory, which I want to call alpha s, and which is, well, alpha s is defined as the square of the coupling, which, well, here I called it E, maybe I should call it G, because this is actually non-abelian gauge theory, so it's not the electron charge, so it's G squared divided by 4 pi. And this obviously comes about because I'm calculating these loop diagrams, and therefore I have a charge G here, a charge G here, and therefore I have a dependence on G square. And dimension dimensional considerations immediately tell me that the log derivative of the log of the operator matrix element can only be a function of the coupling, because there is nothing, everything else is dimensionless. So there is no other place where a scale dependence can enter. Okay, so fine. And this guy here, obviously, I can extract by simply calculating these diagrams and taking the log derivatives. At this point, I noticed the following thing, that the product of the operator matrix element an mu square times the Wilson coefficient Cn, which is a function also of q square, is actually the Mellin moment xn minus 1 of the structure function f2 of x divided by x, right? This is what we had yesterday and where we started from when we did the Wilson expansion. But now you notice this thing that it looks like there is a mismatch of arguments between the two sides of the equation, because the right-hand side is a physical observable. So it can only depend on physically observable quantities. So it can only depend on x and q square. The left-hand side has a mu square dependence here, which is what we just introduced by renormalizing the operator matrix element, and then has a coefficient that depends on q square. But then the only way this can work is if the left-hand side is as mu square independent as the right-hand side. So the only way this can work is that if this guy actually depends on q square through the ratio q square over mu square, and moreover mu square d by d mu square of the product an mu square cn q square mu square is actually equal to 0. Okay? Now, because I said that the scale dependence of an is gamma n times an itself, this equation tells me that mu square d by d mu square of the log of Cn q square mu square must be equal to minus mu square d by d mu square of the log of an of mu square. So it must be equal to minus the anomalous dimension gamma n. See, I'm just substituting the equation up there into the fact that the product is invariant. So the scale dependence of one guy must compensate the scale dependence of the other guy. And this is then something that we call the renormalization group equation for the Wilson coefficient, which we can solve. Solving this equation is standard. It's so this is RG equation, also known as Callan-Simancic equation, and I'm going to solve this equation here, which tells me that mu square d by d mu square of Cn plus, mu square d by d mu square plus gamma n, let me write it like this, of Cn q square over mu square is equal to 0. Okay, I just pulled this on the left-hand side and I did the derivative of the log. Okay, now I notice the following. Just like the operator matrix element beyond leading order depends on the strong coupling, then also the coefficient function, if I calculate it, will depend on the strong coupling. And that's obvious if you think about it, because remember, what this guy is nothing but the structure function of a free quark. The structure function of a free quark at leading order is a delta, so it cannot depend on q square, and therefore it must acquire its q square dependence when we compute it beyond leading order. So this q square dependence here from the coefficient function comes when we will compute the d elastic scattering over a free quark target beyond leading order, which I'm going to do in 15 minutes or so. But this immediately tells us, this simple consideration immediately tells us that this guy depends on q square over mu square, but it also depends on the strong coupling, because in general, we are computing at higher order, and it's only when we compute it beyond leading order that it acquires a non-trivial n dependence. Otherwise, all the coefficients are equal to 1. Now, the strong coupling here must be renormalized because it's one of the couplings of the theory. So this coupling also depends on scale. Now, in principle, at this point, I could have two different scales. I have one scale, which is the scale at which I renormalize my operators, and a different scale at which I renormalize my coupling. So in principle, I could have that. I write this as alpha of mu prime square equals 0, and I choose mu prime square unequal to mu square. I normalize the operator at one scale, and I normalize the coupling at a different scale. And actually, these two different scales have names, which I'm going to discuss later. But there is no special advantage in choosing them different, so I might as well choose this scale also mu square. What people do in practice when doing Feynman diagram calculation is they use dimensional regularization and minimal subtraction. And I don't know how familiar you are with actually, how many of you have performed the loop calculation in dimensional regularization? Okay, half the people. Okay, so half of you have seen this, and probably the remaining half have heard about it. So if you do a calculation in dimensional regularization with minimal subtraction, you have one unique mu square scale, which is the scale which you introduce when you perform dimensional regularization. And a minimal subtraction is kind of funny because the scale which you introduce when you're regularizing the theory then is also the scale at which you renormalize the theory, unlike what I said here, where I said, well, we choose a physical scale at which we normalize the operators, but that's just a practical choice. It just means that calculations are easier, and in that case, it's very natural to have the same mu square everywhere. In a physical scheme, you could say, I normalize my coupling at the value, I don't know, if you were doing QED, I normalize the electron charge at the mass of the electron, for example. In QCD, because you cannot observe quarks, it's much more natural to use minimal subtraction because you don't have an obvious physical scale at which you can define the normalization of quarks. But I'm saying this to say that the choice of scale here is just a convention. It's something to make life easier. So in order to make life easier, we choose the scale here to be the same. And if we choose the scale here to be the same, then you see that the total derivative here actually has both a partial derivative with respect to the direct dependence of Cn over Q square of the direct dependence of Cn on mu square through this ratio Q square over mu square, and also dependence through alpha s. And if you look at it that way, then you can actually rewrite this equation by observing, well, first of all, that you can write this as mu square partial mu square, where by partial derivative I mean the direct dependence, plus partial alpha, partial mu square, partial alpha, plus gamma n, Cn, and I won't write all the arguments of Cn's, which have remained the same. And then I define, let's see, yeah, I guess I can erase this. I define a beta function, which is, by definition, beta of alpha, the log derivative with respect to scale of alpha of mu square. And notice that, first of all, this is something that has to do with the way you renormalize the theory. So while the gamma n is a property of the operator, the beta function is a property of the theory, of the particular theory. It does not depend on whether we are looking at one operator or the other operator, one physical process or the other physical process. The second thing is that beta, again by dimensional analysis, can only depend on the strong coupling itself, because you see everything here is dimensionless, and there is no scale on the left except at the scale through the strong coupling itself. So beta is actually a function of alpha, and if you compute it in perturbative QCD, you actually get that beta in QCD starts at order alpha square, and traditionally people call minus beta the first non-trivial coefficient minus beta naught alpha square. So this minus here is just because that's what people are used to do, plus beta 1 alpha cube plus dot dot dot. Okay, very good. And then The other observation is that because the direct dependence on mu square goes through the ratio q square over mu square d by d mu square of Cn q square over mu square alpha is equal to minus q square d by dq square of Cn q square over mu square alpha. Sometimes people introduce a variable t, which is defined as the log of q square divided by whatever you want. Let's say lambda square, you'll ask, what's lambda square? It doesn't matter. I mean, it's some reference scale that I decide to pick, and then you can write this as minus d by dt, and I'm now writing this as a total derivative because this depends on t only on the first argument, q square mu square alpha. Okay, and then I get a nice equation, which is kind of easy to solve, which is d by dt of c equal beta of alpha partial alpha plus gamma n c Cn, and this is my final form of the Kalan-Szymanczyk equation. So you see I've pulled this, I've replaced this with a beta function, I changed the sign of this, I pulled it on the other side. And this equation is actually fairly easy to solve. I won't have time to go through the details of the solution. You can get it in any field theory textbook like Peskin. Matter of fact, I have compiled a list of references. Maybe Alessandro can provide a list of references, even if I don't have slides. I can either put them on a slide or we can take a picture of my handwritten notes and we'll have them on the website. So I guess at this point, I want to continue on this side because I want to leave the Feynman diagrams over there because I want to get back to them. I leave the definition of the renormalization constants on the top part of the blackboard. And I want to write down the solution to the equation. So if I solve this equation, I find that Cn of q square mu square and alpha of mu square can be written in the following way. It can be written as a function which depends on scale only through the coupling. So some function which I can write as Cn of 1 and alpha of q square. So by this, I mean that this is just a series in the coupling where the coupling is evaluated at the physical scale q square, okay, times exponential, so this is a product, it's not x, I mean, times exponential of an integral from mu square to q square partial lambda square over lambda square of gamma n of alpha s of mu square. So you see what I do is I integrate this equation in two steps. First of all, I integrate out the dependence on the strong coupling, which gives me a strong coupling evaluated at the scale q square. And then I integrate up the dependence through the anomalous dimension. So it's it's a two-step solution. Right. Now, this form of the equation is actually interesting because it tells us how the orders organize themselves, and this we can understand by rewriting the equation in the following way. So we rewrite this as Cn of 1 alpha of q square. Just as a reminder, Cn of 1 alpha of q square is a series that starts with 1. Why does it start with 1? Well, because all Cn's at leading order were equal to 1, you remember, plus alpha of q square times C1 as a function of n plus alpha square of q square times C2 as a function of n plus dot, dot, dot. So this Cn here is a series in alpha that starts with 1. 1 was the leading order result. You remember, the leading order result was that all Cn's are equal to 1. Okay, and then we keep going like this. And okay, then I want to do this integral here, which I can do in the following way. I change integration variable here from lambda to alpha. So I write this as an integral d alpha over beta of alpha from alpha of mu square to alpha of q square, gamma n of alpha. So what did I do here? Well, I noticed that by using the definition of the beta function, which is up here, I noticed that d lambda over lambda is equal to the alpha beta of alpha. So I can think of the beta function as the Jacobian of the transformation that trades the scale dependence with the scale dependence of the coupling. Okay, so I have some scale mu square. I have some coupling alpha. I can use as a parameter mu, but I can trade mu for alpha, and then I parameterize the scale dependence with alpha. And I drew it like this because you know that strong coupling in QCD has this wonderful property that when the scale becomes higher, the coupling becomes smaller, and eventually when mu squared goes to infinity, the coupling goes to zero. So it's in the perturbative region, it's a one-to-one correspondence. I'm just parameterizing this integration variable with alpha, and then I get this thing here. Okay, and then something very nice happens. Because of the fact that the beta function starts at order beta naught. So let me do the calculation here in a corner of the blackboard. I notice that d alpha over beta of alpha times gamma n of alpha, I can write as d alpha minus beta naught alpha squared, what I have down there, plus dot, 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 of course. And then gamma n is a series that starts with alpha, because the anomalous dimension was non-trivial if I calculated at least at one loop, right? Remember the diagrams over there. So this is then gamma n, let me call it 0 times alpha, plus gamma n 1 alpha square plus dot, dot, dot. Okay, I suppose here I could write plus beta 1 alpha cube plus dot, dot, dot. And this I then write as an integral, the alpha. I'm not writing the integration limit. I put them back in a second. So I have gamma naught n divided by beta naught. I have a minus sign here. Alpha over alpha square, so it's 1 over alpha. And then this is all 1 plus order alpha. Okay? So this is minus gamma n divided beta naught log alpha evaluated between q square and mu square. So what I'm getting at the end of the day is that this is nothing but alpha of q square divided alpha of mu square raised to the power minus gamma n divided by beta naught. Okay, because it's exponential. Oh, I'm sorry. Sorry. This is minus gamma. Take it back. This is minus gamma n divided beta naught log alpha of q square divided alpha of mu square. Now I substitute this over there. I substitute it in here. Here I have the exponential. So I then conclude that my Cn of q square mu square alpha of mu square is a series in n. So it's 1 plus C1 n times alpha of q square plus dot, dot, dot. times exponential of this guy, which is what I was writing before. Sorry for doing that. Alpha of q square divided alpha of mu square raised to the power minus gamma n divided beta naught times 1 plus order alpha. Okay? So what I'm discovering is that this scale dependence here, the scale dependence that comes from this exponential, actually starts at order 1. Because you see, look at the way the perturbative expansion is organized. I have a coefficient that starts with 1 and then has an order alpha correction. And then I have this evolution factor, which is alpha, the ratio of alphas to some power, and then 1 plus order alpha. The 1 plus order alpha is what I would get if here under the integral I included the next to leading correction, right? Because you see, here the integral was logarithmic. The next correction would be without alpha, and then this would be linear in alpha. I expand it out, and it would be order alpha. So it would be the same order as C1. So this scale dependence which I found should actually be included in the leading order. Now you say, hang on, but how does this work? So in order to understand how this works, we have to go one step back and remember the starting point. So let me do this, and this is going to lead us to what is sometimes called the QCD improved parton model. So let me take a step back and remind you the logic of the argument that we are doing. So we started looking at the nth Mellin moment of the observable structure function f2 of x and q square divided by x, okay? We concluded that this is the product of an times cn of q square, okay? Then we concluded that beyond leading order, we must actually write this as an renormalized function of mu square times cn function of q square and mu square, and everything here now is dependent on the strong coupling. So there is a hidden dependence on the strong coupling, okay? Then we looked at the scale dependence on this of this guy, which is still written up there, you see. And then we said, well, the scale dependence of this guy must compensate against the scale dependence of this guy. So this guy depends on mu square, this guy depends on mu square, and the two mu square dependencies compensate each other. Now we found a solution here. So the solution which we found consists of writing this as Cn of 1 alpha of q square. Then we have this evolution factor, exponential the alpha beta of alpha gamma n of alpha times alpha of mu square, alpha of q square. And then we have an renormalized function of mu square. Okay? So when we solved the equation, we found that the solution of the RG equation for the Wilson coefficient is some series in the coupling times a factor that depends on mu square. The mu square dependence is only in this factor, is in this integral factor. And you know that this mu square dependence must cancel between these two guys. And in fact, we know that it cancels because remember, the gamma n dependence was precisely the gamma n dependence of an. So the fact that dependence on this gamma n compensates the dependence on mu square of this guy was our starting point, okay? So this means that we might as well change the scale at which we evaluate mu square. So you see, if here we had mu square prime, and here we have mu square prime, it's the same. And let's say here we have some scale q naught square, and I have q naught square, it's still the same. Why not? So in fact, I can go all the way and say, well, why not writing this as Cn 1 alpha of q square times the matrix element an evaluated at q square. Why not? And what's the matrix element an evaluated as q square? Well, it's this guy here, right? So it's an of q square is equal to exponential of the alpha divided beta of alpha, alpha of q naught square, alpha of q square, times an renormalized, evaluated at scale q naught square, where q naught is just some reference scale. So the final conclusion of this argument is that I end up with a new expression for my structure function, this one here, where the nth moment, n minus 1, 0, 1, of the observable physical structure function f2 divided by x is actually given by a coefficient function which is just a series in alpha, okay? So this is just a series in alpha with n dependent coefficients. So the coefficients are just, some algebraic functions of n times an operator matrix element, an, which depends on q square in a well-defined way. How? Well, through this equation, which means that that d by dt, which was, remember, q squared d by d log q square of an is equal to gamma n times an. Notice that there is a plus sign here because there was a minus sign when I took the dependence on mu square, but now this is a dependence on the upper scale, so there's another minus sign. So what I find here is, so now remember the inversion theorem for Mellin transforms. This is the equation for moments. I can turn it into an equation for the structure function, coefficient functions, and the parton distribution, where the structure function is this guy, the coefficient function is the inverse Mellin of this guy with respect to n, and the PDF is the inverse Mellin of this guy with respect to n. Apologies, sometimes I'm writing small n, sometimes I'm writing big N. It's obviously the same n, just being stupid. So what do I get? I get that f2 of x and q square divided by x, measurable q square, is a coefficient function c of x and alpha of q square, where this guy is something that starts with a delta at order alpha s to the 0, and then has some non-trivial function of x at order alpha s, and then a series, times, so convolution, times a PDF that depends on x and q square. And what's the q square dependence of the PDF is the inverse Mellin transform of this equation here. So you see, at the end of this long argument, we ended up with an improved version of our original formula, where now this q square dependence of the structure function comes from this q square dependence of the PDF. And if you're confused, now remember the order counting which I wrote here. So remember that the q square dependence starts at order alpha s to the 0. Right? Because this is alpha to some power. So if I now take this formula here and I write it at leading order, and I leave this here because this is the same formula, so at leading order, I have that f2 of x and q square is nothing but the PDF, because remember, at leading order, this guy is just a delta. So this is just the PDF, which is, however, a q square dependent PDF, right? So this is the leading order expression. And then next to leading order, of course, next to leading order, I'll have that f2 of x and q square is equal to delta 1 minus x plus alpha q square c1 of x plus dot, 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 convoluted with q of x and q square. And let me write leading order next to leading order. What's the difference between Q leading order and Q next to leading order? That Q leading order satisfies, I mean, they both satisfy this equation, but remember, gamma n is equal gamma n 0 alpha plus gamma n 1 alpha square plus dot dot dot. This is leading order. This is next to leading order, and so on. And likewise, in the beta function, beta naught is leading order, beta 1 is next to leading order, and so on. So the upshot of all this is that the scale dependence of the PDF already starts at leading order. Okay, so in the naive parton model, where you want to identify the structure function with the PDF itself, that's fine. That's a correct leading order calculation, up to lots of little factors, charges that I'm sweeping under the carpet and small details. But you must include the scale dependence in the PDF itself, because that's what the PDF had inherited from the scale dependence of the Wilson coefficient. Okay, so this is the so-called QCD improved parton model. Questions up to this point? The 1 over x in F2, yes, you're right, sorry. Here I lost it, so here there is x. And here, I guess I want to have it, it's better to have it here. This is really easy, and then here I want to have it on the left-hand side, because otherwise it's a mess with the convolution. Yes. But by the way, this is the familiar parton model expression that says F2 is equal to x times the PDF. Up to, like I said, I mean, if I do it properly, here I have a square of an electric charge and so on. So this delta is really delta times some normalization, which I'm throwing away for simplicity. You had another question. So good question. So what is Q here? What do I understand? What do I know here? Okay. So if I take a step back, so remember, Q is the operator matrix element. The operator matrix elements are the guys that I can calculate in a quark state, which is how I determine the Wilson coefficients, but I cannot calculate in a proton state. So in a proton state, what AN is the matrix element of my twist 2 operators in a proton, or the matrix element of the complicated Wilson line operator in a proton, which is unknown and determined by non-perturbative physics. What I do know, however, is the scale dependence of this matrix element, because the scale dependence is inherited from the scale dependence of the Wilson coefficient by renormalization group invariance, and that's described by this equation. Now, this scale dependence already starts at leading order. So it starts at order alpha s to the naught, because it's logarithmic. Because you see the integral over there gives log alpha. It does not give alpha. Okay? So this scale dependence at leading order is just given by this factor here. Okay? Now, coming to your question, what happens at next to leading order? Well, at next to leading order, the scale dependence acquires an extra bit, which is this gamma 1, which means that you have this factor, but you also have a 1 plus order alpha. But the 1 plus order alpha, gamma 1 and beta 1 and so on, is of the same order as C1. So at that order, if I include this extra next leading order correction to the scale dependence, I must also, for consistency, include the next leading order next leading order correction to the coefficient function, and the two things compensate each other in terms of scale dependence, and so on. Next to next, I would include C2, which is of order alpha square, and then I would include the order alpha cube correction to the anomalous dimension and the alpha to the 4th correction to the beta function. So, to count powers, remember, at leading order, coefficient function is order alpha to the naught, alpha independent. Anomalous dimension is of order alpha, and beta function is of order alpha square. All these things conspire to give a leading order result, which is this guy here, with the structure function equal to the PDF, and the scale dependence of the PDF given by this factor here, which, if you want to remember something simple which gives the bulk of the dependence, this is what you should remember. Okay? cube, which is usually called beta 1. And by the way, just a little comment, and then I come to the other question. All these leading order coefficients are universal. So for example, earlier I told you we could pick the scale mu square at which we renormalize the coupling different from the scale at which we renormalize the operators. Now, all these coefficients at leading order do not depend on this choice. As soon as you start going to the next order, the coefficients start depending on the choice. So for example, then whether you pick one scale or the other where to renormalize the operators will give you different values of all the coefficients, with the exception of beta 1, because for some argument that it would be a bit long to explain, actually, in the beta function, the first two coefficients are universal. I mean, you know, however you calculate them, you always get the same answer. But instead, gamma n1 and so the anomalous dimension here and the coefficient function C1 will depend on the particular choice of the scale at which the particular choice of scheme or scale in which I renormalize my theory. There was a question. Okay. If I choose, okay, so if I choose mu prime different from mu, I would just get, so if I choose in generally mu prime different from mu, what would happen is that at leading order, everything remains the same. And next to leading order, things change in such a way that the difference between the old calculation and the new calculation is of order of the next excluded order. So if this sounds weird, let me explain what I mean. Yeah, I guess I can use this one. If you remember the definition of the beta function, which was that mu square d by d mu square, yeah, I can spend 5 minutes on this because this is something I wanted to discuss anyway, so I can anticipate it. Mu square d by d mu square of alpha of mu square is equal beta of alpha, okay? This in particular means that if I take alpha of mu prime square, this is equal to alpha of mu square minus beta naught log mu square divided mu prime square times alpha square of mu square or mu prime square. At this order, it doesn't make any difference. Okay, just solve the equation and plug this back. Okay. Sorry, yeah, okay, right? So I can write this as alpha times 1 minus beta naught alpha. So alpha of mu square, 1 minus beta naught alpha log mu prime square, mu square, and this is alpha of mu square. Okay? So let's say I calculate my anomalous dimension gamma n with this new choice. Okay, so I get this gamma n is equal gamma n naught of half times alpha of mu prime square plus gamma n 1 alpha square of mu prime square plus dot dot dot. Okay. So I'm taking the expansion of the anomalous dimension just as an example of what happens. And then I have that this is gamma n naught, and then I substitute this equation down here. So I have alpha of mu square, and then I have minus beta naught, gamma naught n alpha square over of mu square log mu prime square mu square plus gamma n1 alpha square of mu prime square. So you see that these two expressions are the same up to terms of order alpha cube square, provided only this gamma n, so let me call it gamma n bar, and I have that gamma n bar 1 is equal gamma n 1 minus beta naught gamma n 0 log mu prime square mu square. So if I make this new choice in which I choose to renormalize alpha at the scale mu prime, I get, and at leading order, everything is the same, because you see, if I'm at leading order, I can substitute mu with mu prime, and the order is order alpha square, which is why at leading order, everything is the same in any scheme, because I can always change the scale and only produce higher order corrections, which I'm neglecting anyway. And next to leading order, I'm keeping the order alpha square. So when I change the scale here from mu prime to mu, I generate this extra term, which is the same order as gamma 1. But then it's enough to say, with this new choice mu prime, instead of having my old gamma n, I have a new gamma n bar, and gamma n bar and gamma n are related by this relation here, okay, which I can compute. And then, of course, the higher orders will actually be different, because then, of course, you know, I started like this, but then this is also beta naught square, alpha square, and so on. So all the higher order terms will be different, but that's beyond the accuracy of my calculation. So if I pick mu prime instead of mu, then I get that all my coefficients change, and they change in a way which depends on the order at which I'm computing. Okay, and as a matter of fact, unfortunately, this is something I wanted to discuss, but I won't have time to discuss it, so let me mention this because this is quite important. This is a way of estimating missing higher order corrections. So let's say you may have heard about, you know, renormalization and factorization scale variation. So what's renormalization and factorization scale variation? Well, let's say I actually only compute to order gamma 1. And then I say, yeah, but there must be order gamma 2 corrections that I'm forgetting. How big are they? I don't know, but what I do know for sure is that if I had gamma 2 corrections, then the change when moving from mu to mu prime would be of order alpha cube, because I would be one higher order. So one thing I can do is I do my calculation at order alpha square, not alpha cube, and then I vary the scale, and I also vary correspondingly gamma to gamma bar. So the order alpha square accuracy is the same, but I'm producing some extra alpha cube terms, and then I take the difference between the two results with mu and mu prime as an estimate of the missing alpha cube terms. Now, of course, this estimate depends on log of mu prime divided by mu. So you can say, yeah, but how much do I vary mu into mu prime if I want to get a fair estimate of what I'm missing? That's a big, you know, that's a good question. No one actually knows. There is a standard way of proceeding, which is to vary mu by a factor 2, which means varying mu square by a factor 4, up and down, and then, you know, take the difference between the two results computed at the given order as an estimate of the missing higher order correction. And you can ask why 2 and not 3. Well, you know, initially it was a guess, and then people found that in some cases it works, in other cases it doesn't work, and so on. But you get the general idea. So this was a very good question, actually. Yes? Yeah, that's a very good point, and this is obviously something that people have thought about, and in particular, I guess about 10 years ago or so, Matteo Cacciari with a bunch of collaborators, Nicolas Oudot, who was a postdoc at the time, tried this, and unfortunately, what they discovered So the idea is, instead of doing this arbitrary scale variation, now that for many processes we know the first 2 or even 3 or even 4 orders, why don't we just look at the way the series behaves? So what they found then was that this is a very process-dependent statement. So if you look at the way the series behaves, so there are 2 complications. I mean, one complication is that until you go to very, very high orders, at each new order, there is something new happening. So you cannot really predict based on the first 2 orders what will happen at the 3rd order. And if you're confused by this, let me give you a simple example. Say we are doing deep inelastic scattering. At leading order, you have this diagram, okay? And that's it. And next to leading order, we have diagrams like this, say. But then, so this is like a next leading order correction to this process. But then we also have a diagram like this with an incoming gluon. And a diagram like this with an incoming gluon brings in a new operator, which is the gluon operator. And this is not something that you can determine by guessing what happened in the previous order, because this is an entirely new contribution. And then if you go one higher order, there is some new, as people say, partonic channel that opens. So first of all, you really need lots of orders, typically more than we have, because we typically have 3 and things start stabilizing further away. But the other problem is that even for getting this problem, so even if I look at this, then the way the series behave in DIS is very different from the series, from the way the series behaves in Drelian and so on. And this means that if I'm having a new process, it's very difficult to guess what I should do for the new process based on what I know from existing processes. So far, this attempt of guessing the next order based on the existing previous order has not been very successful. But yeah, that's a kind of natural thing to think. More questions? Yes. Yeah, okay, so I would suggest the following. So what I would, this is something, so I have a large number of things that I could possibly discuss, but this was one of the things I wanted to discuss. So it's 10 o'clock now. I propose the following. We take a short break. We try and start again at 10 past 10 or so. What I'm going to do after the break is fulfill my promise, which is to promote all this argument to actual full-fledged collinear factorization. Because so far it's sort of factorization because we have something like this, but we'd like to understand how general this argument is. And then I will come to the sort of questions that Alessandro just asked. So what are the qualitative features of the various PDFs and how can you get them from the data? And then with that, I'll probably stop because I will have run out of time. So yeah, if there are no more questions, we can break now and come back in 10 minutes or so.